Hello, my name is Anna Gyar, and I'm here to show you our work on Mobiwise eco routing, leveraging Internet of Things to fuse multimodal sensor data, which is the result of a transdisciplinary work within the scope of Project Mobiwise. So our motivation was that it is often necessary to distribute traffic in a city to achieve some goals, right? The question is, which goal? Is it to be faster moving from A to B? Is it choosing the distribution that minimizes emissions, or the one that minimizes variability for some nodes moving in the city? So the idea of how do you distribute traffic and which trade-offs are involved, and how to understand them and better to provide better decisions to city planners or managers. So our approach was to design an eco-routing use case. Because you cannot guarantee that everybody follows routing recommendations, we design and build an eco-friendly routing engine for a vehicle fleet. So assuming that only that you make an agreement with a partnership with some fleets like taxis or some buses or ride-sharing services that will actually adopt the recommendations you make. We also focused on the scenario of multiple origins and a single destination. So this maps well to the use case of specific events, or during the rush hour of getting to some specific in the morning, like academic areas, campuses, or business districts, or downtown commercial areas, or in the evening going to large residential areas, right? In all of these cases, you have multiple origins and a single destination. And in terms of optimization criteria, we want to be able to explore different dimensions from travel time and distance to pollutant emissions and noise. Before going into how we actually did it, how would this work in practice, right? You would need to be able to observe what's going on in the city for a certain time, right? Then you need to process this data, this observed data and eventually historic data to predict what's going to happen next. Then you need some time to optimize the routes, so both prediction and optimization will take you some time. And then you can finally serve the routes that you just decided to are optimal. Of course, while you are serving these routes, you will be doing the same process for the next time slot. And while you are doing this yellow step, you will be already preparing the next time slots. Okay, so this is like a pipeline that will be happening at every time slot. So in terms of optimization, we opted for multi-criteria optimization. Why? Because this will enable you to explore the trade-offs. The result of the multi-criteria optimization is a Pareto frontier that will give you the frontier of the minimum cost problem when you try to optimize multiple parameters. So it will give you the points at which, if you actually change any of the parameters, you will definitely provide a worse solution in all others. Okay, so in the others, not necessarily all. So you formulate this linear problem and it is solved to obtain this Pareto frontier. Our next step was to see, okay, which data do we need to solve this optimization problem? Of course, we need road network information, but then we also need to have a traffic information for all edges in our network. We need to have emission information for all edges, and we also need to have traffic demand for that destination that we are considering. Okay, the traffic demand, of course, being the number of vehicles that start at each possible origin. The first point, so the road network, is static, but the other three are dynamic. So these are all the result of the steps of data observation and prediction that I just showed you in the previous slide. And our next step in the design was to see how we could realistically obtain this data in a city. So if we think very futuristically, all of this will be available, and then you can do your optimization. But our goal in this project was to see how we could actually try to build this system in a city in sort of a near future without a clean slate design of the city. So how do we get this data? So to obtain the per link information for all edges, the traffic. We can use inductive loops. Some exist on some edges. There are also some traffic cameras on some other edges. And we also have some vehicle probes, so you have some fleets that are instrumented with positioning systems. And you can, of course, merge all this different data to obtain more precise per link traffic information, at least more precise or more granular. The same is valid for vehicle dynamics, because you can use this. This is useful for estimating, for predicting the emissions. You can use acceleration, the speed, the amount of stop and go events. And to obtain this, you also need either to have vehicle probes or combine that with a digital twin and some driving models on your digital twin. The digital twin is a simulation, as reliable as possible simulation of what's happening in the real world. Then the information, to obtain emission information for all edges, you can use the per link traffic information and different types of models, either digital twin and micro models or meso models, or you can combine also this information with environmental sensors that are installed nowadays everywhere. And the traffic demand, you can obtain it from origin destination matrices or out of other information that you know about. So how would our eco-routing use case architecture look like to aggregate all that information? So first of all, this would be our routing service, requiring also a traffic prediction and emission prediction. So I'm modeling this. Probably there is no entity that will have all this information or all the algorithms to solve this. So we designed this as a microservice-based architecture so that different entities can operate the different pieces, and you can actually exchange one of them to another without changing the whole of the system. So this is a more robust solution, robust to changes in the stakeholder ecosystem. And then, taking the city of Porto as an example, we embedded data from buses and taxis, which are already in different providers, with some data collected from a crowd sensing app. We need to do pre-processing to just put all this data in a consistent format. And then we also embedded inductive loops from the municipality, which is in yet another data format. So this is our traffic sensing data. We also have in Porto some environmental sensors collected to municipality broker and some other monitoring protocols. So we use then Fireware to aggregate all of this. Fireware is an open source Internet of Things platform that can enable sort of quick deployment of the pieces we need. The core piece is this context broker, and Orion is the name, and you can feed your data into that broker, directly from the municipality data or from using an IoT agent. This context broker exposes the data as a standard data format, which is this NGSI data. This means that all other pieces above this interface, they can use this data easily because it's in a standard format. So we also had some persistent modules from this Fireware infrastructure. They are developed and you only need to sort of install them to be able to use it. So now the data flow, so our position and speed per edge data can be exposed in the context broker together with the rest of the data. Traffic prediction can consume this data and then republish speed and volume data. The emission prediction will feed this data and produce the emissions per edge, which will be the input to our routing algorithm. Of course, then this is available through a RESTful interface for users to access the recommendation. Now, we implemented a simpler proof of concept. We used the inductive loops in the city of Porto to calibrate a digital twin in Sumo. This produced the per edge information, and the traffic demand. and was input into the multi-criteria optimization, which produced what you see here, the Pareto frontier, these blue dots. Okay, this Pareto frontier was, so you see also the original result, and this Pareto frontier shows you the trade-off between having, a shorter time will cost you more total length per vehicle, and of course, if you have shorter paths, you have a larger time per vehicle. But so the decision maker would just have to pick one of these points and then implement it as the route being served. However, because we are here using static data for the emissions, we actually validated again by feeding our new routes into the Sumo digital twin and obtaining the simulation output, which are the red dots that you can see here. So here you can see the difference between what is actually the optimal and what would more likely happen in reality. Again, this difference is caused by the lack of information about the changes. So when the optimizer changes vehicles, there is no update of the emissions and congestion state. That's why when you simulate, you obtain slightly different results. So let me now show you our tool for city managers. So you have a login page, of course, and you can choose, it's a viewer for our simulation. So now we're taking a simple example, and then you can choose optimization parameters for demonstration purposes, choosing time and length. And we are going to see videos of what has been previously simulated. So these were previously recorded, and you can see here the initial status, and then you can see the Pareto frontier, and you can see the results of after the simulation, after optimization. By clicking on any point, you can see on the right side a visualization of what happens, so on all dimensions. Okay, so you can compare the initial status with one specific solution. Below you have the same information in a table format, and even below that you can have a look at the baseline and the optimized simulation to try to understand what led to the changes, what caused the changes in the various parameters. The simulations are synchronized, as you can see. You can also run actually live. You'll run the simulation live, so this will start the optimization and this proof of concept pipeline. So let us now choose a different set of parameters to optimize. Actually also a different setting in Porto. Now in the rush hour, you will see now the result of the simulation, of the optimization and the simulation, and again you have in green in the middle the initial value, and you have the other, the simulated points. If you click on the right side, you can see the changes in all the dimensions for the specific case, although the length increases with respect to the original solution in green. The optimal solution will improve every other dimension, and of course the solution from the optimizer is better than the one simulated in the digital twin. Nevertheless, you are actually able to improve in every dimension besides the traveled kilometers. So to conclude, we have conceived and designed an eco-routing service for fleets. We formulated the problem as a multi-criteria optimization, proposed a modular architecture for integrating heterogeneous sensors, and implemented a proof of concept using a digital twin. Finally, we built a tool to support decision-making by city managers or by researchers analyzing the results. In the future work, we plan to improve emission air quality modeling that can be embedded in the optimization problem and understanding the changes proposed by optimization using this tool. So please contact us here during the session or afterwards for any questions you might have. Thank you.